The term erythro and trio is used to define substituents in Fisher projection, and these two, they're going to appear in your homework, so just want to explain what is that. So erythro is whenever you have substituents on the identical substituents on the same side of the Fisher projection, so that is going to be erythro because you do have your bромines in this case on the same side of the Fisher. And trio is whenever you have your identical substituents on opposite sides of the Fisher projection. So this is an example over here assigning the configuration on each chiral center. So these are problems. So I did put a lot of problems in there just for you to practice before you start working your assignments. If you have your molecular model, please use your molecular model to assign the configurations for each. Now, I am asking which are enantiomers, which are mesocompounds, and which are diastereoisomers. When you have a question like this, please make sure to figure out the configuration first around the chiral center. Once you figure out the configuration, you go by the definition. If they are enantiomers, they should differ by all chiral centers. If they are diastereoisomers, they should differ by at least one chiral center. And mesocompound, you are able to draw simply a plane of symmetry that cuts the molecule in half. So you should have groups basically that are the same. So I'm going to start here. I have two chiral centers. So you have your hydrogen, do your configuration. That is going to be, I'm going to use this color. So that is going to be basically 1, 2, and 3. This is priority 1. The whole thing here is priority 2. This is priority 3 going 1, 2, 3. This is going to be an R configuration since hydrogen is behind. Here, again, it's easy whenever your hydrogen is behind, your lowest priority group behind, you can easily set the configuration. So going by 1, 2, and 3 like this is an R configuration again. So this structure 1 has an RR configuration. Structure 2, we're going to do the same thing, so that is easy. That stays the same. See, it stays the same, so it is R. Now for 3, these two changed. So it should be an S. Let's go ahead and see. Now, if you have your molecular model, just rotate to make sure that this hydrogen is behind. If you don't have your molecular model, now I'm going to swap these two together. So now this hydrogen becomes the OH, and this OH becomes the hydrogen that is behind. So that is going to be 1, that is going to be 2, that is going to be 3. So going by 1, 2, and 3 like this, so now I'm getting the configuration of the enantiomer. So I need to reverse it. This is going to be an R configuration for the enantiomer. So I need to reverse it to get the actual configuration for my molecule. It is an S configuration. RR, RS, they differ in one chiral center, so 1 and 2 are diastereoisomers. You do the same thing over here. So you're going to end up having 2, 3 are diastereoisomers because they differ in one chiral center. This is the chiral center that they differ in, 2 and 3. And 1 and 3 are enantiomers. Where's 1 and 3? 1 and 3 are enantiomers because they differ in both chiral centers. Okay. So without drawing the structure, label the compounds as enantiomers or diastereoisomers. That is easy. RS, RR. So carbon number 2 stays the same. Carbon number 3 changed. These are diastereoisomers. RS on carbon 2. RS. So basically RR changed into SS. These are enantiomers because they differ into chiral centers. And with this one over here, this is a diastereoisomer because they differ in at least one chiral center. Which of the following cyclic molecules are mesocompound? To be meso, you should have same groups and you should be able to draw a plane of symmetry. So look, here I cannot draw a plane of symmetry because if I draw a plane of symmetry, the CH3s are not in the same plane. So I'm not going to have this part of the molecule aligning with that part. So no plane of symmetry, not meso. Here, yes, there is a plane of symmetry because the CH3s, they align with each other. They are on the same side. Here, no, because the chlorine and the OH, they are different groups. Okay. Chiral or meso compound. So all what you need to do is figure out if you can draw a plane of symmetry. See, if I draw a, let's take this one over here. So okay, if I take, this is the plane of symmetry, so if I take this plane of symmetry and set it over here, I'm still gonna have the OHs are gonna be in opposite planes, so that is not gonna be a plane of symmetry cutting the molecule into two equal parts, or two parts that are basically the same. So this is not gonna be a meso compound, it's gonna be a chiral compound, and that chiral compound has 1, 2, and 3 chiral centers. Also, the meso compound has, if you have, where's my meso? If there is a meso, this one meso, this is the meso over here. The meso has basically 2 chiral centers in here. As I said, not all chiral centers are optically active. If you have a chiral center and you're able to draw a plane of symmetry in the molecule, then the molecule will be optically inactive. It's gonna be a meso compound. It will not have a mirror image. Again, this one over here, I cannot draw a plane of symmetry in it, so this is chiral. For that guy, I can draw a plane of symmetry, and the plane of symmetry is through the OH, the carbon, and the OH, which is behind. So through that, these bonds over there, it's easy to view it if you build up the molecular model for it. You don't have to build up the molecular model for the benzene. Just put any groups instead of benzene. But if you build a molecular model for this guy, you can easily see that you can draw a plane of symmetry through the OH, the 2 carbons in the OH, and you can simply have that part aligning with the second part of the molecule. Now, same thing over here. I can simply draw a plane of symmetry. So this is my cyclohexane chair conformation. I can draw a plane of symmetry, and that plane of symmetry, see how I drew it? It's around the carbon, 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 carbon. Since I have my OH down and OH down, this is axial, this is equatorial, those are going to be both in the same plane in there. Okay, so so in that case, I'm going to end up basically getting an achiral compound. Now notice here what I said. I said that it's achiral, I didn't say it's meso. The reason why, because I don't have basically a chiral center. So this is a carbon over here that is surrounded by 2 groups that are different, but see, these are the same. CH2 is connected to CH2 is connected to the CH. So these carbons, since they have the same connectivity, they are the same. So I don't have 4 different groups. So that carbon is not a chiral center. That carbon is not a chiral center. So the whole molecule is going to be an achiral molecule. There is no chiral center for. So definitely there will be no mirror image for. Now with respect to here, this carbon, I have a CH3 pointing up, CH3 pointing up. I can simply draw a plane of symmetry, see, along that axis there, cutting the molecule in half. So this is going to be a meso compound. This guy is a chiral center. I have a chiral, a chiral molecule. I have 2 chiral centers in here. This is basically, so I have 2 chiral centers in here. This guy over here is is basically not a chiral center, but these 2 are chiral centers in there, and I cannot draw a plane of symmetry, so the molecule is going to be chiral. Same thing over here. I have a chiral center there. Okay, and I do have a chiral center over here. So this has 2 chiral centers in that case. See, so we have, yeah, this is not a chiral center because these 2 groups are the same as these 2 groups. You see it? So these 2 groups are the same. Let's see. You know what? Let's take a look at this guy over here. This is connected. Yeah, this is not a chiral center because you know what? There is a CH3, and this is a chiral center. So you have 3 chiral centers in this case with this one. Okay, so draw all possible stereoisomers, label the enantiomer and the diastereoisomer as we did before. So you just go over that. I did write the detailed explanation for. So as we did before for all the examples that we went through, we're doing the same thing over here. Just make sure that the moment you can draw a plane of symmetry, then the molecule will exist as a meso compound. That is in case it has a chiral center. So see here, it doesn't have a chiral center, so the molecule will only exist in a form of stereoisomers, which are cis and trans. If you can draw a plane of symmetry, then the molecule will exist as a meso compound only if it has chiral centers. Only if it has chiral centers. If it does not have a chiral center, here it doesn't, because these two are the same. It doesn't have a chiral center, then the molecule will exist in its two stereoisomers as cis and trans if it is a cyclic. So determining the relationship between the molecule. If I give you a molecule and ask you, what is the relationship between? Are they basically enantiomers, diastereoisomers, identicals? Just follow this chart over there. So if you have molecules that are not identical, check if they are isomers or not. If they are isomers, then check if they are constitutional. If they are not constitutional, they are definitely stereo. If they are stereo, are they enantiomers, mirror images, or are they diastereoisomers? So let's have an example over here. Okay, these two. So we're gonna select. Okay, state each of the compounds. Are they enantiomers, diastereoisomers, constitutional isomers, or identicals? So so again, you locate your chiral center. This is your chiral center, and this is your chiral center over there. The thing here that I want you to do is do the configuration and see, because the configuration is the easiest. This is S, this is S, so I know that these are the same, identical. If I have SR, then it's going to be mirror images of each other, enantiomers. So here I have the 1,4 isomer, here I have the 1,3 isomer, these are constitutional. For this one, do the configuration, RRSS, then this is enantiomer. For this guy over here, these two, do the configuration again. So again, RRSS, these are mirror images, they are enantiomers. So as you can see, I'm doing the configuration to check the relationship between these molecules. So with these two over here, you have the same molecular formula. You have opposite configurations at one chiral center. Let's check the configuration in here. This is the hydrogen, and this is the hydrogen over there. So this is going to be 1. Yeah, it's going to be 2, and that is going to be 3. And I'm going by 1, 2, and 3. See, I'm going by 1, 2, and 3 over there. So 1, 2, and 3, and that is going to be in an S configuration. So this is an S. So definitely this guy is an R. Let's double check. Hydrogen is in front. So what I would do is I would swap this group with this group over there. So I'm having 1, 2, and 3. This is an S, but since I swapped it, then I need to reverse it, and it's an R configuration. SR, this is enantiomers. This is a trans, this is cis. Immediately, no need for me to figure out the configuration. The moment you see trans and cis stereoisomers, these are diastereoisomers. Trans, cis. So trans and cis over here, these are diastereoisomers. Okay, no need for you to figure out the configuration. This is up, down, trans. Up, up, cis, diastereoisomers. More examples in there, even if you do the Fisher projection. If you have the same configuration around the chiral center, you guys, immediately, these are going to be the same. If you have, again, same configurations, then this is going to be the same. Carbon that bears the NH2 is an S configuration, and carbon that bears the OH is an R configuration. So if your configurations are the same, immediately your structure is identical. To figure out the configuration in the Fisher projection, you locate your chiral center, you set the priorities around the chiral center. So the oxygen here is 1. This whole thing is going to be 2 because this is a carbon nitrogen versus a carbon hydrogen. So that is going to be 2 and that is going to be 3. Going by 1, 2, 3 like this, it's going to be an S, but hydrogen is in front. So that is going to be an R configuration. You do the second the same. Redraw each Newman projection, determine the RS configurations, then determine the molecules if they are related or not. Remember when we switched the Newman projection to a staggered conformation, we said that all the groups that are on the side, these are in front, these groups are behind, and then whatever is on the horizontal, on the vertical line, these are in plane. So you simply, all what you need to do is just redraw that and figure out the configuration, and then from the configuration you can figure out if the molecules are identicals or enantiomers or diastereoisomers. Now the last topic that we want to explain is the racemic mixture. What is a racemic mixture? A racemic mixture is an equal amount of two enantiomers. So when you combine, when you end up having 50%, when you end up having 50% R configuration, 50% S configuration, this is an equal amount of enantiomers, 50% R, 50% S, then we say that the molecule exists in the form of a racemic mixture. A racemic mixture is optically inactive. Why is that? Because one pair of enantiomer one enantiomer is gonna rotate the plane of polarized light to the right, and the other one is gonna rotate the plane of polarized light to the left. So by rotation of the plane of polarized light to the right and to the left, because one of them is going to be dextro-rotatory, which is positive. The other one is going to be levo-rotatory, which is negative. And one thing that I want to say, very important, to determine if it's dextro or levo-rotatory, rotating the plane of polarized light to the right and to the left, you cannot do this with the R and the S. So R does not mean that it rotates the plane of polarized light to the right. This is not true. The positive and the negative, normally these are the information that I provide you with. I give you with, unless you're doing the actual experiment, you figure out these values in there. But normally, if the compound has, if the chiral center, this is the configuration around the chiral center, the rotation of the groups around the chiral center. The plus and the minus is the rotation of the plane of polarized light. This is completely different. So these two are not related, you guys, okay? So a racemic mixture basically is a mixture that has 50% R, 50% S. This means that one enantiomer will rotate the plane of polarized light to the right. I don't know which one. It's either the R or the S. But definitely, if one of them rotates the plane of polarized light to the right, the other one has to rotate the plane of polarized light to the left. So because the two enantiomers rotate the plane of polarized light, one to the right, one to the left, to an equal extent, but in opposite directions, the rotations cancel out. And there will be no rotation for the plane of polarized light. This means that the molecule will be optically inactive in this case. So let's have an example. If you have A that has a mirror image B, okay? And I want to look at the physical properties. I know that A and B are enantiomers of each other. Enantiomers have the same physical properties. They have the same melting point. They have the same boiling point. The difference between enantiomers is only in the optical rotation. One of them rotates the plane of polarized light to the right. I don't know which one, but one of them rotates the plane of polarized light to the right. The other one has to rotate the plane of polarized light to the left. Now, if I have 50% R configuration, 50% S configuration, then this means that half of the enantiomers are going to rotate the plane of polarized into one direction, and the other half is going to rotate it to the same extent, but in opposite direction. So it's as if the plane of polarized light did not basically rotate at all. So A alone has a rotation of the plane of polarized light. B alone rotates the plane of polarized light, but an opposite in sign to A. But if I combine A and B, this is what a racemic mixture is. A racemic mixture is a combination of these two enantiomers, A and B. If I combine them together, then I'm going to have 50% R, 50% S. Then the optical rotation, one of them is going to rotate the plane of polarized light to the right, the other one will rotate it to the left. Then the plane of polarized light will end up not being rotated at all. Enantiomers, they do have the same physical properties. Enantiomers normally they have different properties that depend on the shape of the molecule, but the physical properties are the same. Same melting point, same boiling point, and same density. Let's have an example. Okay, here you go. So let's have an example over here, tartaric acid. So with tartaric acid, what do we have here? This is the same example that I told you that I'm going to come back to it. So with tartaric acid in here, we ended up, for tartaric acid, if you remember, with tartaric acid we had two chiral centers. And when we figuring out the stereoisomers, we said we had 4 stereoisomers, but when we drew them, we ended up having 1 pair of enantiomers plus 1 meso compound. This is when we drew them, okay? We had 1 pair of enantiomers and 1 meso compound in there because we were able to draw a plane of symmetry. Now for the pair of enantiomers, those pair of enantiomers in there, if you do the configuration, one is going to be RR and its mirror image is going to be SS. So here you go. This is going to be 50% R, 50% S. So when I combine these two enantiomers with each other, I'm going to end up getting a racemic mixture. So A alone has a melting point same as B. So this is A, this is B. So enantiomer A has the melting point same as B. It has a density same as B. The only difference is the optical rotation. One rotates the plane of polarized light to the left, the other one rotates the plane of polarized light to the right in this case. Okay, in this case, but again, there is no relationship between positive and the S. The S is the rotation around the chiral center. The positive is the rotation of the plane of polarized light. So if you combine the two enantiomers, the A and B, combining A and B, then the melting point is going to be different. This is for the racemic mixture. The density is going to be different, and the optical rotation is going to be 0. This means that racemic mixtures are always optically inactive because they are made up of 50% R, 50% S enantiomers. So the rotation of the plane of polarized light does not exist, does not happen. So this is why the molecule is said to be optically inactive. I am given the S-alanine and I am asked that under the structure over here, I do have all the physical properties, starting with what is the melting point of the R isomer of alanine. Is going to be the same. The melting point is the same as the S. How does the melting point of the racemic of the R and the S compare to the melting point? Basically, the melting point of the racemic is different because the melting point of the racemic is basically more. It is way more than the melting point of the individual R and the S isomers. What is the specific rotation of R aniline? Well, I'm given the specific rotation for the S. So the specific rotation for the R is going to be the same value of the angle but opposite sign. It's going to be negative 8.5. Now with respect to the optical rotation of the racemic mixture, it's going to be 0 for the racemic mixture. It's optically inactive. Label each of the following as optically active or inactive. Pure aniline, that is optically active. An equal mixture, this is racemic, 50% R, 50% S. Then definitely this is going to be optically inactive. A solution that contains 75% S, 25% R alanine. We're going to come back to this one over here after I explain the enantiomeric excess, the EE. I'm gonna come back to this guy over here. Okay, so where are we? Here you go. So for optical purity, we're gonna explain this guy, do some problems, and come back to that. So sometimes in the lab we have neither a pure enantiomer nor a racemic mixture, but instead we have a mixture of two enantiomers, in which one enantiomer is present in excess of the other. So that is called enantiomeric excess. It's optical purity. It's the measurement of how much one enantiomer is present in excess of the racemic mixture. Okay, so EE, the optical purity or the enantiomeric excess. This is the EE. It's a measurement of how much one enantiomer is present in excess of the racemic mixture. And this is basically the formula for it. So EE is equal to the percentage of one enantiomer minus the percent of the other enantiomer. This is the EE. So consider the following example. If a mixture contains 75% one enantiomer, 25% other enantiomer, another enantiomer. So the E is going to be 75 minus 25, that is 50%. What does that mean? This means that there is 50% excess of one enantiomer over the racemic mixture. So, so it's going to be 50% excess of one enantiomer over the racemic mixture. So if it is 50% excess over there, I know that my racemic mixture is going to be the other 50% here. And the racemic mixture is in equal parts of A and B. So A is going to be 25% and B is going to be another 25%, right? So if I want to consider the percentage of A, then A is going to be that 25% from the racemic mixture plus the 50. So A is going to be 75%, and the remaining 25% that is going to be for the B. For a given EE value, calculate the percentage of each enantiomer present. So if I'm given 90% EE, 90% enantiomeric excess means that I have 90% excess A and I have 10% racemic mixture. So whatever I am given, that is going to be for A, and the leftover is going to be for the racemic mixture. And I know that the racemic mixture is going to be 5% A, 5% B. So now if I want to calculate the percentage of A will be 90 plus 5. So it's going to be 95A and it's going to be 5% B. Do the same for 99% and 60%. What is the EE for each of the following mixtures of enantiomers A and B? So I am given 95% A, I'm given 5% B, subtract them from each other. You get the EE. Do the same over there. Okay. I can also, if I am given the optical rotation for the pure enantiomer versus the mixture, I can calculate the enantiomeric excess. So this is another formula in there. Let's say pure cholesterol has a specific rotation. So I'm given negative 32 for the pure enantiomer. It says pure, negative 32. And then I'm given the optical rotation for the mixture, which is negative 16. put them in the formula in there and get the enantiomeric excess. Coming back to whatever we were talking about. Where is that, Rana? Okay, so whatever we were talking about here, a solution that contains 75% S, 25% R aniline. This guy is optically active. Why? Because it doesn't contain 50%, 50%. See, the percentage over here, if we want to check the enantiomeric excess, you have more S than R. Look, you have more S than R in this case. Since you have more S than R, it is optically active. If it was 50% S, 50% R, so no, it is going to be optically inactive. This equal mixture of R and S. But here the mixture is going to be different. If I want to calculate the enantiomeric excess in this case, I know that it's going to be 75% S. Now, and the 75% is going to be S in this case. 25 just divided by 2 is going to be 12.5. So add the 12.5 to the 75, and that's going to be basically the S isomer is going to be 87.5% enantiomeric excess, and the rest is going to be for the R isomer. As long as the S and the R are not equal percentages, then your molecule is going to be optically active. Okay, that will end the chapter. So please solve the top hat assignment and the OWL assignment for this chapter. If you have any questions, please let me know.